In this video, we're going to do some review problems to get ready for the Chapter 12 test on vectors. So first, let vector AB be a vector with initial point A at 3, -1, and terminal point B at -2, 2. So we're going to answer a bunch of different questions there. First, the component form. I'm going to draw a picture of this. We don't have to have this, but it's kind of nice, I think, to see what's going on here. So A is going to be at the point 3, -1. So there's 1, 2, 3, and -1 is going to be right there for A. And B is going to be at -2, +2. So that's going to put B right there. We're going from A to B. So it's going to have, we say, the tail at A and the tip at B. So to find the component form, we're going to go tip minus tail. So our vector AB is going to be, and we're going to take the ending point. So B will go a -2 minus 3 for the x component, and then we'll go a 2 minus -1 for the y component. And so that's going to make that be a -5 and a +3. So that is the component form of vector AB. To find the magnitude of AB, oops, I dropped the second part of that. The magnitude of AB is just like Pythagorean theorem. We're going to get the square root of, and then we'll square and add the components. So that's going to be the square root of 25 plus 9, which will make that the square root of 34. So that is the magnitude of vector AB. So for the slope, part C, the slope of vector AB, we can look at rise over run. So we can see that we are going to rise 1, 2, 3. So we're going to go up 3, and we're going to go left, which is a negative 1, 2, 3, 4, 5. So that's going to make the slope be a -3/5. The direction angle, theta, of vector AB is going to be, we can think, we're going to have to do a little interpretation here. So looking at this kind of triangle that we formed, we're imagining now that we move this actually into standard position. So I'm going to change colors here. So if we move our vector, which we know has component form -5, 3. So if I go 1, 2, 3, 4, 5, and 1, 2, 3, I didn't plan that very well. So in standard form, our vector is going to be here. So this is our angle. We can use it as a reference angle in this triangle as long as we get the correct signs there. So that's going to be a -5 and a 3. If we can do an inverse tangent, we also know that the hypotenuse is that magnitude of the vector is the square root of 34. And we're really going to have to do some interpretation anyway. So if we go, for example, the inverse tangent of our y over x are -3/5. And I'm going to grab my calculator and make sure that I am in degree mode, which I'm not. So now I am. So I'm going to go an inverse tangent of a -3 divided by 5. And that is going to be a -30.96 degrees. Now, that, remember, is it's our calculator's programmed to give us that quadrant 4 angle. So if we think of our reference angle as being 39.96 degrees, then our angle, which again is going to be this quadrant 2 angle, is going to be 180 minus that 39.96. So I'm going to add the 180 to what I have on calculator screen, and that's going to be 149.04 degrees is our angle theta, the direction angle of our vector AB. So when you do these, you have to keep in mind which quadrant we're in, and it may take a little bit of kind of reasoning to get what that actual angle coming from the x-axis is going to be. So now we want a unit vector in the direction of AB. So remember, in general, what we get is a unit vector is going to be our vector AB divided by its magnitude. And since our magnitude of our vector is the square root of 34, then we're going to get, what was our original vector, negative 5, 3. So we're going to get our, if I can get this to cooperate, negative 5 over the square root of 34, and 3 and square root of 34, and we have to rationalize, so we're going to call that finally negative 5 square root of 34 over 34, comma 3 square root of 34 over 34 is our unit vector, and that's a vector of length 1 in the direction of vector AB. So then, to get a vector of length 17, we will multiply our unit vector by that 17. So I picked 17 because I knew it would cancel with 34. So we can do that. And since 17 goes into 34 twice, we can call this negative 5 square root of 34 over 2, comma 3 square root of 34 over 2 is going to be a vector of length 17 in the same direction as vector AB. And the ij form of our vector AB, since we knew its components were negative 5, 3, then we can write that in ij form as negative 5i plus 3j. So remember, you can write it in these angle brackets, they're called, as component form, or you can write it in the ij form, but do not mix them up. So if you try to write something like this, you'll lose a point because that's just an abuse of notation. Okay, so don't do that. Okay, let's see what else we got here. So an object at the origin is acted upon by two vectors, vector u and v, with direction angles theta sub u and theta sub v respectively. Find the direction and magnitude of the resultant force. So by resultant force, what we mean is the sum of those vectors. So r, the resultant vector, is going to be u plus v. So what we want to do first is to write u and v in their component form. And so u is going to be in its component form. It's going to be 40, the magnitude, times the cosine of its direction angle, and then the magnitude times sine of its direction angle. And in this case, we actually know what the cosine of 30 and the sine of 30 is, so we can actually simplify this a little bit. Cosine of 30 is square root of 3 over 2, and sine of 30 is 1/2. And so if we cancel the 2 with the 40, we're going to get 20 square root of 3 for the horizontal or x component, and 20 for the vertical or y component. So that's our vector u. In a similar fashion, v is going to be its magnitude, 70, times the cosine of its direction angle, 45 degrees, and the magnitude 70 times the sine of its direction angle. And we also know the sine and cosine of 45. That's for each of them, that's going to be square root of 2 over 2. And so we can cancel here as well and get for both of those 35 times the square root of 2. Whoops. So we have 35. Trying to bring my pen back up. Square root of 2 for both the x and the y component of vector v. So then to add them, we can just add their components. And so that's going to be our 20 square root of 3 plus 35 square root of 2, and 20 plus 35 square root of 2, just adding their x and y components. And you were free to just leave it like that. I think I'll just leave it like that for now. To find its magnitude, so we want the magnitude and the direction angle. So the magnitude of the vector r, the resultant vector, is going to be the square root of 20 square root of 3 plus 35 square root of 2 squared, plus the 20 plus 35 square root of 2 squared. So I'm going to enter all of this into my calculator, and we can do this just in one line if we're careful. So I'm going to go square root and then parentheses 20 square root of 3 space out of the square root plus 35 second x squared square root of 2 arrow outside the square root and parentheses square that, and then go plus the new parentheses 20 plus 35 square root of 2 arrow outside of that, parentheses squared, and then I can just hit enter, and I'm looking at 109.129. 109.129. So there is our magnitude of the resultant vector and our direction angle. So we can take the inverse tangent of y over x. So that's going to be the 20 plus 35 square root of 2 all over 20 square root of 3 plus 35 square root of 2. And this is all positive, so we're going to be in quadrant 1, so we don't really have to worry too much about, do we have to get a reference angle? So I'm going to go inverse tangent, and then I'm going to go up parentheses 20 plus, it should be a 35, I wrote a 3. Let's call that 35 square root of 2. 35 square root of 2. Right arrow, close parentheses, because that's all in the numerator, divided by new parentheses, 20 square root of 3, right arrow out of the radical, plus 35 square root of 2, right arrow, close parentheses, and then I need another parentheses for the inverse tangent. I think I did that right, and then it looks okay because I'm getting about 39.6 degrees. 39.6 degrees for our direction angle. Okay, let's see what we've got up here next. So now a plane sets off with a speed of 350 miles per hour and a bearing of 120 degrees. So this is what we will call airspeed. So our airspeed vector, which I'm going to call A, is going to have a magnitude then. So that vector is going to be its magnitude, which is 350 times, and now I need to draw a picture. So we're going to have to go from a bearing to a direction angle, do the computations, and then go back to a bearing again. So remember, a bearing goes from due north 120 degrees clockwise. That might be a little too much. So 90 degrees would take us to the x-axis. So this is our bearing right here of 120 degrees. Now that's going to make our direction angle be, we can either go this way or we can go around there. So it might be a little easier to recognize that direction angle as being a, since 90 degrees took us to the x-axis, that's going to either be a negative 330 or a positive 330 either way. I'm just going to call it a cosine of negative 30 degrees for now. And then it's going to be 350 times the sine of negative 30 degrees. So that's our airspeed vector. And we don't know what the wind speed vector is. That's what we're looking for here. We're actually end up, after the wind acts on our plane, we're going to be traveling at 340 miles per hour with a bearing of 110. That's going to get us to our ground speed vector. I'm going to give that a different color. So let's say that our ground speed vector is going to be its magnitude, which is 340 times, and now I'm going to have to change that bearing of 110, which would be a little bit short of that 120. So this is going to be our ground speed vector here. So it's got a bearing of 110, and that means its theta is going to be, its direction angle is going to be a negative 20 degrees. So we're going to get a cosine of negative 20 degrees, and then 300, that's not a degrees right there, 340 is the magnitude times the sine of negative 20 degrees. So that's going to be our ground speed. Now, I'm going to call wind speed, I'm going to let it be blue. So that's the vector we're looking for, and we know always that ground speed is equal to airspeed plus the wind speed. So solving that just like an algebra problem, we're going to get that our wind speed is going to be the ground speed minus the airspeed. So in this case, our wind speed is going to be the 340 cosine of negative 20 minus the 350 cosine of negative 30, comma, 340 times the sine of negative 20 minus the 350 times the sine of negative 30. Okay. So I'm going to go to our calculator here, to my calculator, and I'm going to put in first the x component. So I'm going to go 340 cosine of a negative 20 and minus the 350 cosine of a negative 30 and hit enter, and I'm getting 16.387, it looks like 387 rounded to 3 decimal places. And then I'm going to do the same thing for the y component. So 340 sine of negative 20 minus 350 sine of negative 30. And that looks like, see, 340 sine of negative 20 minus 350 sine of negative 30. And I'm getting a 58.7 0.713, rounded to 3 decimal places. So there's our wind speed vector. We're trying to find its actual speed. So the wind speed is going to be the magnitude of this vector. And so I'm going to go to the square root of, and it's going to be the square root of, and I'm going to not use the rounded version. I'm going to go ahead and capture all the decimal places of accuracy here in a moment. Okay, so I've got the square root of, I'm going to go up and capture that 16 point whatever, and then I'm going to square that, then plus, and then I'm going to go and capture the 58 point whatever, and square that, and then hit enter, and I'm getting 60.957. 60.957. That's going to be in miles per hour. It's kind of a breeze in Laramie. Now we're going to try to figure out what the direction angle is, and then once we get the direction angle, we're going to get the bearing. So I'm going to use theta for the direction angle first. And so we can see that these are both positive. So our wind vector is going to be up here in quadrant 1. It's going to be doing something like this. That's pushing that green vector over to the yellow vector. So to find the direction angle, we're going to take the inverse tangent of that y, 58.713, but I'm not going to use the rounded value, over 16.387. Everything's positive, so that should give us a quadrant 1 angle. So I got inverse tangent. I'm going to go up and capture the 58 point all that, divided by, go up and capture that 16.38, whatever that is, and then close the parentheses, and I'm getting 74.4 degrees. 74.4 degrees. Now that's our direction angle, theta. So if this angle right here is our 74 degrees, then our angle beta, I'm going to extend this out here, our direction, or rather our bearing, is going to be 90 minus that. So our bearing is going to be 90 minus the 74.4 degrees. And so I'm going to go 90 minus, go up and capture that. And that's looking like about 15.6 degrees is the bearing of our wind. So our wind has a speed of about 61 miles an hour and a bearing of 15.6 degrees. That's pushing our plane off course. All right, let's do our crane problem. Here we have two cranes supporting a 13,000 pound weight, and we're trying to find the tension in the cable of each crane. So that's really saying find the force of the cable in each crane. So we have, we can think of this as being a vector that's going this direction to support that weight. We have another vector going in this direction, and I'm not necessarily saying that their lengths are representing their magnitudes at this point, because I'm not really exactly sure which one is going to be holding up more weight, more of the force, which is a weight. And then we also have this weight that's going down. So what we have then is that the sum of the forces acting around this point are going to equal 0. So it's in equilibrium, that is that 13,000 pound weight is suspended there in the air. It's not moving up or moving down or moving right or moving left. That means that the sum of all the vertical components and horizontal components must be equal to 0. So I'm going to give these some names. I'm going to call this vector V1, this tension vector, the one that's coming out to the upper left there. And I'm going to call this vector V2. That's the one that's coming up and to the right. And then we have our weight vector down here, which is going straight down. We're going to break these into their components. So we know, for example, the weight component is going to be 0 in the horizontal, and all 13,000 pounds of force are going to be in, and it's going to be a negative, are going to be in the vertical direction. Since it's going down, that's going to be a negative 13,000. Now the V1 we know is going to be its magnitude, which I don't know yet. So I'm going to rename this here. I'm going to just say that the magnitude of vector 1, I'm going to call just M1. It's just a little easier to write than writing that double bar V1 with the arrow on top. Similarly, I'm going to say the magnitude of vector V2, I'm going to call M2. So in its components, our vector V1 is going to be its magnitude, which is M1, times the cosine of its direction angle. Now remember, vector V1, we can see that this little angle in here is 37 degrees, but the direction angle for V1 is going to come from the positive x-axis counterclockwise to that point. So that angle is really going to be 180 minus the 37. And so that will account for the correct positive and negative sign for the components of our vector. So 180 minus 37 is going to be 143 degrees. Now in our mind anyway, we can see that the cosine of 143, an angle in quadrant 2, is going to be a negative number, which would make sense that the negative component of the horizontal component of vector V1 should be pointing to the left, which is a negative direction. And in a similar fashion, we're going to say its y component is going to be M1 sine of 143 degrees. So that's going to be our component form of vector V1 for right now. We're going to have to figure out what the M1 and what the M1 is. Now vector V2 is going to be its magnitude, which I'm going to call M2, times the cosine of its angle, but that angle is exactly the 20 degrees that we see. So that 20 degrees is exactly what we want for writing the component form of vector V2. And likewise, we'll get M2 times the sine of 20 degrees for its vertical component. So we know that the sum of the vertical components are going to be 0, and the sum of the horizontal components are also going to be 0. So the vertical components are going to be vector V1, which is M1 cosine of 143 degrees, plus the horizontal component from vector V2, which is going to be M2 cosine of 20 degrees, and then plus the horizontal component of our W vector, which is just 0, is going to equal 0. So there's one equation. We're going to do the same thing now with vertical components. So that means that M1 times the sine of 143 degrees plus M2 times the sine of 20 degrees. And now we're going to bring in the vertical component of our wind vector. So minus the 13,000 is going to be equal to 0. So what we want to do here is maybe a little substitution. So we have our two equations and two unknowns. We don't know M1 and M2. So on the first equation, if we are going to get M1 by itself, we can subtract that M2, so it'll be a minus M2 cosine of 20 degrees to the other side. and then we'll divide by the cosine of 143 degrees. And so we'll get that M1 is going to be the cosine of 20 over the cosine of 143 times our M2. I'm going to slide this up a little bit. So now we're going to go to our second equation, and we'll replace the M1 by our cosine of 20 over cosine of 143 M2, and that's going to be times the sine of 143, and then we have our plus M2 sine of 20 degrees, and I'm going to move that 13,000 to the other side, which will now make it a positive 13,000. So on this left side, we now have just one variable, M2. I'm going to factor that out. We can think of, and you don't have to do this, but I think it's kind of a nice little organizational scheme, and we can declutter it a little bit. So the sine 143 over cosine 143 we can write as the tangent of 143, still times the cosine of 20 degrees, and then we've got the plus sine of 20 degrees, and that's equal to our 13,000. So solving for the M2, I'm going to slide this up a little bit. So we're going to divide all of that stuff to the other side. So we're going to get 13,000 over the tangent of 143 times the cosine of 20 plus the sine of 20. So all of this is going to go into our calculator. So I've got the 13,000 divided by, and then in parentheses, tangent of 143 times the cosine of 20 plus the sine of 20, and I'm going to close the parentheses on the sine 20, close the parentheses on the denominator, and I'm getting here, let's see, I'm getting a negative 35,510. I know that can't be right, but I think if I go back here, let me change my color for a minute. I neglected this negative sign right here. So let's see if we can retrace that. That would have made this be a negative, and so this would be a negative there, and so that should be a negative there, so that should be a negative there. I'm going to try that again. So let me see if I can insert my negative sign in front of that tangent. Okay, and then I'm going to try it over again. So now I'm getting something that looks a little more reasonable. So now, after I've made that adjustment, I'm seeing 12,379. That's going to be 0.428. 428. That's a force, so that's going to be in pounds. And then once we know that, we can go to our M1, which is going to be right here. And so M1 is going to be, let's see, we're going to get our M2, so we're going to go negative cosine 20 divided by the cosine of 143, and then I'm going to take that times and then grab that answer that we got for M2, and that I'm getting now to be 14,565.915, and that's going to be in pounds. So that is going to be the magnitude of our tension vectors. Let's see, is that what I wanted to find? Let me make sure. Can we name and find the tension in the cable of each crane? So we've done that. So that's our force, which is our tension in each of those cables for each of those cranes. Very good.